Welcome to our lecture video, everybody. Today we're going to finish chapter 6. Specifically, we'll talk about chapter 6, sections 3 and 5. Now, even though there are only 2 sections this week, the reason for that is because these 2 sections are quite complicated and extremely important for this section on, or this chapter on matrices, and another name for it is linear algebra. And I mentioned this last week that linear algebra is what you will need to use quite a bit as you go on to econometrics, and which is a very powerful tool we have in economics. So it is essential for you to not only understand, but be able to solve problems in linear algebra or matrices. Okay, so now 6.3, okay, let's start there, introduces what's called the determinants. Okay, determinants. And then later on, we'll talk about something called Cramer's rule. But a determinant of a matrix is very important in solving matrix equations. And of course, today it will be all about that. So, so let's first start with the easier case where I've already showed you last week, where we determine, or we figure out a determinant of a 2x2 matrix, right? So if you have a matrix that is A11, A12, A21, and A22, again, these subscripts just describe to you the location in the matrix for each element, right? A11 means first row, first column. A22 is second row, second column, and etc. Okay, and the determinant of this matrix, okay, and is denoted by A with the 2 vertical bars around it, and it is not an absolute value. Okay, in linear algebra, or the world of matrices, this is the determinant. And for a 2x2 matrix, this is very easy. Okay, this equals A11 times A22 minus, okay, A21 times A12. So essentially, you just multiply on the main diagonal, A11 and A22, then subtract the product of the other diagonal of A21, A12. And that's it, okay? And now, let's do a couple of practice questions really quick. Okay, so examples. Again, when I give you examples, I hope you pause the video, try to solve it on your own, then proceed to view the solution to make sure you get it right. So if we have a matrix that is -2, 3, -1, and 3, okay, then its determinant in this case would be -2 times 3, okay, minus -1 times 3, because we multiplied in this direction first, then we subtracted the product in this direction on the diagonals, okay? So if you do that, this equals -6 minus -3, which is +3, so that gives you -3. So -6 plus 3 gives you -3. Okay, that's the determinant of this matrix. Now, what if we have another matrix that is 2, -3, -4, and 6? Then its determinant, B, is then 2 times 6, so the product on the main diagonal, okay, minus -4 times -3. So that's the product on this diagonal. Okay, that gives you 12 minus, okay, -4 times -3 is +12, and it gives you 0. Okay, now we'll talk about what it means to have a determinant of 0 later on in this chapter. Okay, but a determinant can be 0, and that is legitimate and okay, but it can mean something when it comes to solving a system of equations using matrices. Okay. All right. Now, another concept we want to introduce, okay, the first one is called a minor. Okay, so if we have matrix A to be an n by n matrix, so we're not specifying how big, but it has to be square, right? So it's either 2 by 2 or 3 by 3 or 4 by 4, etc., because the number of rows and number of columns equal each other. Okay, and if you have, okay, I and J are, okay, numbers between 1 and n. So that means I and J are somewhere between 1 and n. So so that then A of I and J, okay, is an element of the matrix A. Okay, so all we're saying is if this is a 3 by 3 matrix, then I and J are numbers between 1 and 3, then A of I and J would be an element in this matrix, right? So if you have A of 2 and 3, that means it's the element on the second row and the third column, okay? So if this is the setup, then we say, okay, the minor of the element A, I, and J, okay, is the determinant of the n minus 1 times n minus 1 matrix formed from the original matrix A, okay, by deleting, okay, the ith row and the jth column. Okay, now let's look at an example, right? So let's say, okay, we have a matrix of A that equals -5, 3, 2, then 1, 0, -1, -3, 1, and 0. Okay, so it's a 3 by 3 matrix. Now, if I have a question that says, okay, find the minor of A1, 2, okay? So I know that the definition right above this might seem like a bunch of gibberish. So let's look at what we mean by here, okay? So first of all, we want to find A1, 2. So that means it is the element that's in the first row. That's what that 1 tells you. Okay, then the second column right here. So number 3 is your A1, 2. That's the element in the first row and second column position. Now we said find the minor of it. And according to what we just wrote, we said the minor is the determinant of the matrix formed from A by deleting the ith row and jth column. In this case, it's the first row and the second column. So what we mean is you take your pencil and you cross out the first row and the second column because that's where A1, 2 exists. That's how A1, 2 is formed, is by crossing these by these two, this row and this column meeting each other. So we get rid of this. So you get, okay, an alternative matrix. Call this, B. Now B is 1, -1, -3, and 0. Okay, so that's what's left of A, and A is no longer 3 by 3, now it's 2 by 2. So according to our definition, okay, the minor of A12 is then the determinant of B, right? So that means then the minor of A12 equals the determinant of B, which is which is 1 times 0, right? That's the product of this diagonal, minus, okay, -3 times -1, which is the product of this diagonal, okay? And if you do that, this equals 0 minus +3, which is -3, okay? So that's how you find the minor of a matrix. You take whichever element you're finding the minor for, and then subtract the row that element is on and the column that element is on. Once you delete that row and that column, whatever matrix you have left, you find the determinant of it, and that will be the minor of that particular element you began with, okay? So again, we'll use this concept in just a little bit when we try to solve a matrix equation. So keep in mind what it is, just like how you should keep in mind how to find the determinant of a 2 by 2 by now. Okay, we'll in a minute we'll talk about how to find the determinant of a bigger matrix. Okay. Now another concept we want to introduce is something called the cofactor. Okay, so the cofactor, okay, of, let's see, the cofactor again of an element, or of the element, excuse me, Aij, just like before, is -1 raised to the I plus jth power times, okay, the minor of Ai and j, Aij, okay? So as a result, you can see if I plus j is even, okay, then the cofactor for Aij is the same as the minor of Aij. Okay, because if I plus j is even, then -1 raised to the even number power will be +1. So +1 times something is itself. Okay, so if the position of your element, the number of row plus the number for the column added up to be an even number, your cofactor is your minor. However, if I plus j is an odd number, okay, then the cofactor, okay, is the negative of the minor. Okay, because if I plus j, let's say it is A23 you're looking at. So that's the element on the second row and third column. Well, 2 plus 3 is 5. So -1 raised to the 5th power is still -1. So -1 times the minor is going to be the negative of the minor. Okay. So again, let's look at the example. Okay, so we're using the same matrix we just used, where it's -5, 3, and 2, then 1, 0, -1, -3, 1, and 0, just like the last example. Okay, now if I want you to find the cofactor of A23, okay? So again, pause the video and see if you can figure it out. Okay, now To solve this, we know A23 means it's the element on the second row and third column, which is right here. Okay, this is the second row, third column. To find the cofactor of it, we know that we need to find the minor of it. So we eliminate the second row and the third column, and then we call what's remaining, as matrix B. Then you have -5, 3, -3, and 1. So the cofactor, okay, equals, well, let's say of A23 equals -1 raised to I plus j's power, in this case is 2 plus 3's power, okay, times the minor of A23, which is the determinant of B, okay, determinant of matrix B, so that is -5 times 1, okay, minus -3 times 3. Okay, so that is, again, the product of these two elements timed together minus the products of these two elements timed together. And if you do that, okay, -1 raised to the 5th power is still negative. And then you have -5 times 1 is -5 minus, okay, -3 times 3 is -9. So that becomes plus +9, which gives you, okay, negative of +4, which is -4. So that is the cofactor of A3, which is the negative of the minor of A23, okay? So again, we'll talk about how to use determinants, minors, and cofactors in just a few minutes. But now I want you to be able to understand how to calculate them, not necessarily what they are yet, but how to calculate them. Okay. All right. Okay. Now let's look at how to find the determinant of an n by n matrix. Okay, so we're moving on from a 2 by 2. Okay, now that's because, well, as you can imagine, okay, your world is going to get a lot more complicated than just a 2 by 2 matrix. And in fact, in econometrics, as you move on, the entire class is about evaluating systems of equations that often have dozens, hundreds, even if it's pure theoretical, then can be n variables and n equations. You're trying to solve them all together at the same time. And I have mentioned that, well, to solve a system of equations using linear algebra or matrices, you need to find the determinants of the determinant of such a matrix. So you definitely will be dealing with mostly, excuse me, bigger than 2 by 2 matrices. And in this class, for the purpose of calculating by hand, you can go up to as big as 3 by 3 or 4 by 4. I probably won't, push you higher than that because it gets pretty tedious. You can still do it, of course, by hand, but it gets pretty tedious after that. So nonetheless, it is extremely important for you to understand how determinants and minors and cofactors are used to solve systems of equations in matrices, in linear algebra. Okay. All right. So, okay. Now, the way to calculate your determinant for a m by n matrix is kind of interesting. Okay. So this is, to find the determinant of an n by n matrix, okay, you need to expand along a fixed row or column, okay, And the result actually does not depend on which row or column is chosen. You can use any row or column in a matrix to figure out the determinant of this n by n matrix. Okay, so let's look at how that works. And then I'll give you an example to talk about what we mean by that. Okay, so to expand along, okay, the ith row, okay, and then that means each element in that row okay, is multiplied by its cofactor. Okay, so now you know cofactors are used to calculate determinants. Okay, and minors are used to calculate cofactors. That's why we had to introduce those ideas. Okay, and okay, and the n products are then added. What I mean by that is, in the ith row, because this is an n by n matrix, we have n elements, right? Because in each row there are n elements, in each column there are n elements. That's why it's an n by n matrix. So you add up every element multiplied by its own cofactor, and there are n of them. Then you add all those element times by its cofactor products up together, and that gives you your determinant. Okay, again, I know this is extremely abstract and confusing it. For now, I'll give you an example in just a minute. Okay, now if you want to expand along a column, let's talk about that as well, right? To expand along the Jth column, okay, again, each element of that column, which there are n of them because it's an n by n matrix, okay, is multiplied by its cofactor, okay, and the n products from elements timed by cofactors are then added. Okay, so it's really the same thing you do whether you choose a row or a column. You just take each element in that row or column, multiply it by its cofactor, which is found by using -1 raised to, the I plus jth power times its minor. Okay, again, I know you probably have forgotten about how to do that. Let's look at an example. Okay, so I'll say you have a matrix that's A equals, okay, -1, 3, 2, 2, -2, 0, 0, 4, 1, 5. Okay, now the way to find the determinant, so find, okay, a determinant. Okay, the way to find the determinant of this matrix is you can pick any row or any column and then take every element in that row or column, multiply by its cofactor, okay, and then add everything together. Now, because you can pick any row or any column, it is smart to find the easiest row or column to calculate. And in this particular case, you can see that the second row right here has 2 zeros as elements. Since we're going to be multiplying the elements to their cofactors, having zeros will really simplify your calculation because 0 times anything is 0, right? So I would choose the second row because any row or any column will do the same trick and they will give you exactly the same result. So I'm going to use the second row. And what I get is that, the determinant then equals every element in the row times its coefficient and then add it up together. So the first element is -2 in the second row, okay, times its coefficient, which is -1 raised to, because -2 is a to 1, right? Because it's the second row, first column element. So this is -1 raised to the third power because it's 2 plus 1. Or if you want to be more specific, let's do that. Okay, so it's -2, okay, times -1 raised to 2 plus 1 power, and then times the determinant of, times this minor, which is the determinant of getting rid of the second row and the first column and see whatever you have left, which is 3, 2, 1, 5, right? You're with me? Because the minor, again, the minor is eliminating the row and the column your element is on, and then calculating the determinant of whatever remaining matrix it is. So if we do that, this is -2 times -1 times 3 times 5, which is the product along this diagonal, minus 1 times 2, which is product right there, okay? And that gives you +2, because -2 times -1 is +2. +2 times 10 minus 2, which is 8, and that gives you 16, okay? Wait, sorry, not 10. Sorry, that's 15. My apologies. I made a math error there. Okay, so 15 minus 2, that's 13. 2 times 13 is 26. Okay, apologize for that. So that is the determinant of A, the 3 by 3 matrix that we had initially. Now, the reason it's this simple is because this is then 0 times its cofactor plus the third 0 and times this cofactor. But since it's 0 times them, we just didn't have to calculate those as well. At all. So that is one trick to keep in mind, okay, to figure out how to calculate the matrix, okay. Now, let's do a more sophisticated one, okay, and help you figure out how to do this, because 3 by 3s are still kind of easy. Let's do a 4 by 4, okay. So let's say we have a matrix B that is a 4 by 4. It is 4, -2, 3, 0, okay, and 2, 1, -1, 3, 3, 0, 1, 1, 2, -2, 0, 0. Okay, now find its determinant. Okay, again, you can pick any row or any column to do this, and the easiest way for me is to use the last row because it has 2 zeros. That means you can get rid of 2 calculations in your calculation of multiplying elements times with their products. Okay. So I'm going to pick that row to use. Okay, so now we say B determinant equals then 2, okay, the first element right here, okay, times its cofactor, which is -1 raised to, this is the 1, 2, 3, 4, fourth row, first column, so it's -1 raised to 4 plus 1 power, then times the matrix that comes from eliminating the 4th row and first column, because that is that's its minor. Okay, so again, I'm going to get rid of this, but I'll just show you it's -2, 3, 0, 1, -1, 3, 0, 1, 1. Right? Because this is the matrix that we simplified from B by eliminating the first column and the second, the first column and the fourth row. Okay, so then we want to add the second element in the fourth row, which is right here, okay, -2. So we want to add -2 times -1 raised to the fourth row plus the second column power times its minor, okay, which is eliminating the second row and the second column in the fourth row. Okay, if you do that, again, I'm gonna get rid of these lines, but if you do that, you have a 4, 3, 0, 2, -1, 3, and 3, 1, 1. Okay, I hope everybody's with me. Okay, so let's keep going then. This is, okay, -1 raised to the fifth power is -1. So we have -2 now. -1 times 2 is -2. Okay, -1 times 2 is -2. Then, okay, now I have to find the determinant of this 3 by 3 matrix right here. And well, the way to do that, again, is to find the easiest row or column to use. You can see here, you know, we have 2 rows with 0, the first row here and the third row there, but okay, the third row has 2 1s, and that's going to be an easier calculation. So I'm going to pick the third row. Okay, so we have to do this all over again. The determinant of this 3 by 3 matrix is 0 times this cofactor, okay, which is from this point right here. But I'm going to just leave it like that because it's going to equal to 0 plus, okay, 1 times -1 raised to, this is the third row plus the second column, okay? So then times is cofactor, which is obtained by eliminating this row and this column. So you get, and I'll get rid of those lines, -2, 0, and 1, and 3. Okay, and then plus the third one right here, okay, 1 times -1 raised to, this is the third row plus third column, times the its minor, which is by eliminating the third row and the third column. Okay, so we have that 2 by 2 matrix, okay, which is -2, 3, 1, and -1. Okay, so that is, this whole thing is this one term right here, because we're trying to find the determinant of that 3 by 3 matrix, which is a minor from the 4 by 4 matrix we had previously. Okay, so that's that term. So we still have this entire term here that we need to deal with. So let's do that. Okay, so this then is plus, okay, -2 times -1 raised to the 6th power right here. The 6th power is an even number, so that's +1. So this is +1 times -2, okay, it's still -2 times, now here you can see I have just this 1 0 here. So in this case, you can choose to either do the first row or the third column. We haven't done a column, so let's do a column. And I'm going to use this third column. Okay, so -2 times, okay, the first element is 0 times this cofactor. Okay, I'm going to leave that there because both of these will just go to 0. So there's nothing I need to do. But then I do 3 times -1 raised to, this 3 right here is in the second row and third column. So second row plus third column, then times its minor, which is eliminating second row and third column. So that gives you 4, 3, and 3, 1. So I'll get rid of these lines. So you have 4, 3, 3, 1 plus, okay, that last element in that column is 1, okay? So it's 1 times -1 raised to. This 1 is at third row, third column. So it's 3 plus 3 here times its minor, which is by eliminating the third row and third column. Okay, so that gives you 4, 3, 2, -1. Okay, so 4, 3, 2, -1. And this whole line is this part of your initial, okay, calculation. Okay, so now I know this looks complicated, okay, but bear with me because the method is the same and the practice is good for you. Okay, so this equals -2 times, okay, the first thing in my bracket is just 0 because it's 0 times its cofactor. I don't even have to calculate its cofactor. Okay, plus the second term here is 1 times -1 raised to the 5th power, which is -1, times, okay, finally the determinant of a 2 by 2 matrix. You know how to do that one, right? That is -2 times 3 minus 1 times 0, okay? Plus, okay, now this term right here, which is 1 times -1 raised to the 6th power, which is still 1, and that times -2 times -1 minus 1 times 3. Okay, so that's the first that's the first line you have right here. So that's that line. Okay, and then plus the second -2 times, again, the first term is 0 in, because this right here, okay, plus 3 times -1 raised to the 5th power is -3 times, okay, 4 times 1 minus 3 times 3, that's the determinant of the 2 by 2 matrix, plus, okay, 1 times -1 raised to the 6th power, which is 1, times 4 times -1 minus 2 times 3, and that's it. Okay, so that is this whole line of an expression. Okay, now let's simplify it even more. You have -2 times, okay, now it is -1 times, so this is -6, and this is just 0, so you have -6 times -1 plus, okay, then 1 times, okay, -2 times -1 right here is +2. +2 minus 3, that's what it is, and you have -1. Okay, that's again this whole line right here. And the second line right here, that simplifies to -2 times, okay, the first term is 0, is gone. The second term is -3 times 4 minus 9, okay, so that gives you -5, so you have -3 times -5, plus here is -4 minus 6, so that's going to give you -10, okay, so that is -2 times, okay, -1 times -6 is +6. +6 minus 1, that gives you 5, but we'll leave it that way for now. Plus -2 times, okay, -3 times -5 here is right here. That is, okay, +15, then minus 10. And that finally gives you -2 times 5 plus negative 2 times 5. And so that is negative 10 minus 10, which is negative 20. Okay, so this negative 20 is the determinant of this B matrix that we started with, the 4x4 matrix that we started with. Okay, so I know this is a lot of tedious calculations, but this is how you get it done. And I hope I did not make any math error. If you got a different answer from this, go through this problem carefully. If you think I made a math error, make a note, and then we'll talk about it in class. But hopefully I didn't. Okay. All right. Now let's talk about some properties of determinants. Okay, so one is that a constant can be factored out of each of the terms in a given row or column when computing determinants. Okay, so you can factor a constant out of a row or column when you calculate the determinant. What I mean is, for example, if you have 2, -1, 15, and 5, and you can see this equals 2, -1, then 3 times 5, and 1 times 5, right? Because 3 times 5 is 15, 1 times 5 is 5. Then that can be written as 5. You can pull that 5 out of the determinant and then leave 2, -1, 3, and 1. Okay, now recognize that here all these are determinants. These are vertical lines you have on the outside. These are not matrices, right? Because we have talked about before, you can multiply a matrix by a constant, but if that's the case, you can multiply that constant into every element in that matrix. But with a determinant, you pull that constant out of one single row or one single column. Okay, now this you can verify by saying, okay, so if I were to calculate this equals, okay, 2 times 5 minus 15 times -1, which is 10 minus -15, and that gives me 25. Okay, now here this equals 5 times 2 times 1 minus 3 times -1, and that equals 5 times 2 minus -3, which is 2 plus, 2 plus positive 3, right? 2 minus -3 is 2 plus positive 3, and that gives you 25, right? So they equal exactly the same. So you can pull a common factor out of one row or one column, right? For example, if you have, 4, 7, 12, 9, and that, the determinant of that is the same as saying 4 times 1 and 4 times 3, then 7 and 9. So you have a common factor in a column, so you can pull that out as 4 times, okay, 1, 7, 3, 9. Okay, again, you can verify that saying this equals 4 times 9 minus 12 times 7, which gives you 36 minus 84, which is -48. Okay, then this right here equals 4 times, okay, 1 times 9 minus 3 times 7, and that is 4 times 9 minus 21, which is 4 times -12, which is -48. Okay, so you can pull a common factor out of a column and make it multiplying the whole determinant in this manner as well. Okay, so it's the same. So that's the first property of how to work with a determinant. If you see a common factor in a row or a column, you can pull it out and set it outside, and that will make your calculations a little bit easier, okay? And now the second property is that you can interchange two rows or two columns, and that will change the determinant by a factor of -1. Okay, so interchanging, okay, two rows or two columns or two columns will change the determinant by a factor of -1. Okay. All right. So for example, what I mean by that is if you look at the determinant of 2, -1, 15, and 5, just like we looked at earlier, and somehow, okay, you switch the two rows, you change it to 15, 5, and then 2 and -1. You just flip the two rows. Okay. If you see, then this equals, okay, we already did this 2 times 5 minus 15 times -1, which equals 10 plus 25, which is 25, right? And then this equals 15 times -1 minus 2 times 5, which is -15 minus 10, and that is -25. So by switching the two rows, okay, you have changed the determinant from 25 to -25, or by a factor of -1, okay? Similarly, if we look at the same example we did, where you have now the same example, similar example, 3, -2, 7, and 1, finding its determinant versus, okay, if we switch the columns this time, -2, okay, -2, 1, and 3, and 7, so those are switched, okay? So this equals 3 times 1 minus 7 times -2, which is 3 plus 14, and that gives you positive 17. And this equals -2 times 7 minus 1 times 3, which is -14 minus 3, which is -17. Again, by switching the two columns, you get a negative determinant. Okay, so if you are somehow seeing matrices with two rows or two columns switched, and this works with a bigger matrix. If you just switch two of the rows or columns, the same thing will happen. Okay, so you'll have a negative of the previous determinant that you were looking at. Okay, finally, the third property about the determinant is that, so the determinant okay, is unchanged, okay, by adding a multiple of one row, okay, or column to another row or column. Okay, for example, if you have 3, -2, 1, and -1, and the determinant of this is the same as if you want to make it a little bit easier and get a 0 out of this matrix to make your calculation easier. So you can do, -3 times row 2 added to row 1. If you do that, it becomes, 0 and 1, and 1 and -1, right? Because -3 times row 2 makes this number -3 right here, okay? And -3 plus 3 gives you this 0, okay? And then -2 right here, plus this is -1 times -3 is +3, and -2 plus +3 gives you this +1. That's how we got these numbers. Okay. But anyway, so these two, you're adding the multiple of row 2 to row 1, and these two determinants are going to be exactly the same, right? Because this equals 3 times -1 minus 1 times -2, which is -3 plus 2, which is -1. Here, this equals 0 times -1 minus 1 times 1, which is 0 minus 1, which is -1. Okay, so you can then, when you face a certain matrix, and if you can spot by adding a multiple of one row or column to another will simplify a certain row to give you a bunch of zeros, then do that first before you calculate the determinant, right? So if you can find somehow a way to make a bunch of zeros appear in your matrix by row manipulations like this, then definitely do that to simplify your life. Okay. All right. So now, okay, let's kind of hit the punchline by giving you what's called the Cramer's rule. Okay, so Cramer's rule says that, I guess, again, let's start with the two variable, two equation linear systems, okay? And if you have, so let's do two variables, two equation systems. Okay, so what I mean by that is if you have two equations where it's ax plus by equals e, and then cx plus dy equals f. Okay, you have two equations you can solve. And then what's going to happen is that using Cramer's rule, you know that x equals dx over d and y equals dy over d, where, okay, d is the determinant of the coefficient matrix. The coefficient matrix. Okay, so that means it's this determinant of A, B, C, and D. Okay, and that's what D is. Okay, then dx is the determinant, okay, of the matrix formed by replacing the column of x coefficients with the column of constants. So what I mean by that is it's the determinant of, okay, instead of A and C, which are coefficients for right in front of x, right, and except for these two terms, what we're going to do is to replace them with the constants of E and F right here. So it's the matrix D of x is the determinant of the matrix E and F, because you use the constants to replace A and C, then B and D. Okay, similarly, okay, dy is the determinant of the matrix replacing the y coefficients of b and d with e and the constant. So you have a, c, and e, and f. So you replace these two with the constants right here. Okay, so that's how you get the determinant of that matrix. So, and then if you do dx divided by d, that will give you the value of x. If you do dy divided by d, that will give you the value of y. That's Cramer's rule in the simplest case of two equations and two variables. Okay. Now, of course, here you can see that d is in the denominator of calculations of x and y. Okay, so that means, okay, we're assuming that Cramer's rule will only work when d, this d right here, or this d right here, is not 0. Okay, but when d is 0, then the system is either dependent or inconsistent. Dependent means you have an infinite number of solutions, and inconsistent means there's no solution at all. Okay, so this is a key thing to remember. Okay, so if d equals 0, okay, and both dx and dy are also 0. Okay, well, I'll write it out, 0. Okay, then the system is dependent. Okay, that means infinite number of solutions. Okay, now if d is 0 and at least one of dx and dy is non-zero, okay, the system has no solution. Okay, that is when there's no solution in existence. Okay. All right, so let's look at again some examples. Okay, so let's say that, first example, I have two equations where it's 4x minus 5y equals 3, negative 3x plus 7y equals 1. And then solve this using Cramer's rule. Okay, so well, we know Cramer's rule says x equals dx over d and y equals dy over d. So, okay, let's look at it. Okay, and then we say, okay, d is the determinant of all the coefficient matrix. So that means it's all the numbers in front of x and y's, right? So this is then the matrix of 4, negative 5, negative 3, positive 7. And that equals 4 times 7 minus negative 3 times negative 5. And that is 28 minus 15, which gives you 13. Okay? Now dx is replacing the x coefficients with the constants, right? So that means it is the determinant of 3, 1, then negative 5 and 7, right? I replace the coefficients of 4, negative 3 in front of x with the constants of 3 and 1 from the two equations. So this equals 3 times 7 minus, okay, 1 times negative 5, and that gives you 21 plus 5, which is 26. Okay, then dy equals replacing the y coefficients with the constants. So you get, okay, 4, negative 3, then 3, and 1. Okay, and find the determinant of that, which is 4 times 1 minus negative 3 times 3, which is 4 plus 9, which is 13. Well, if you do plug all these numbers in, you get x equals 26 over 13, which is 2. and y is 13 over 13, which is 1. Okay, so x equals 2 and y equals 1 is the only solution to this system of equations. And of course, to verify, you can plug these numbers back into these equations to make sure both stand. And that's one good way to check if you made a mistake in your calculations. Okay, and in this case, I have verified my number, so I know they're correct. But you're welcome to try it on your own, of course. Okay, now let's look at another example. Let's say now you have another system, which is negative x plus 2y equals negative 1, and 3x minus 6y equals 3. Okay, so again, we want to find d, which is the determinant of negative 1, 3, 2, and negative 6. And that is negative 1 times negative 6 minus 2 times 3, which is 6 minus 6, and 0. Oh, all of a sudden, we have a 0 in the denominator, right? Because x equals dx divided by d. Y is dy divided by d. And we just figured out d, the denominator in both equations, are 0. So we know that this system is either dependent or inconsistent. Now we need to figure out if dx and dy are both zeros, right? So dx, again, is to replace the coefficient of in front of x's with the constants, okay? So to do that, we have negative 1, 3. These constants happen to equal exactly the same coefficients right there, right? So that then 2 and negative 6. And you can see this looks exactly like the determinant you're trying to calculate in D, so we know that equals 0. Okay, then dy is replacing the coefficients of y with constants. So that means you have the matrix, the determinant of negative 1, 3, and negative 1, and 3. Okay, because this column here is this column from the constants. Okay, so this equals clearly negative 1 times 3 minus 3 times negative 1, also 0. Well, now because dx and dy are both 0, when d is 0, then that means this system is dependent, which means it has an infinite number of solutions. Okay. All right. So that's the Cramer's rule, which is very useful in the simple two-variable, two-equation case. Okay. Now let's look at the full Cramer's rule. Okay. That can be applied to any n system of n equations with n variables. Okay. So let's say you have a system of n equations. Okay, with n variables, and instead of calling them x through z, because you only have 26 letters, we call them x1, x2, dot, 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 all the way to xn. That way you don't have to run out of numbers, okay? And then you can express the system by saying this is a11 times x1 plus a12 times x2 plus dot, 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 plus a1n times xn equals, let's call it b1 to be your constant. Then the second equation is a21 x1 plus a22 x2 plus dot, 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 plus a2n times xn, that equals b2. And then these equations keep going all the way to an1 times x1 plus an2 times x2 plus dot, 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 plus ann times xn, and that equals b of n. Okay. So this is a whole system of n equations with n variables. Okay, so then the solution to this whole system, according to Cramer's rule, okay, is x1 equals, okay, d of x1 over d, and x2 equals d of x2 over d, and dot 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 to xn equals d of xn over d. Okay, where d is still the determinant of the coefficient matrix, right? So d is the coefficients a11, a12, dot 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 to a1n, okay? Then a21, a22, dot 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 to a2n, then all the way to an1, an2, dot 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 to ann. Okay, d is this determinant. Okay, now similarly, okay, dx1 is when you replace all the coefficients of x1s, okay, which is this first column right here, with the constants in your from your equations. Okay, so dx1 is when you replace the coefficients of ax1s with constants. So you have b1, b2, dot 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 to bn, and then a12, dot 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 to a1, 1n. That's terrible. 1n, then a22 to a2n, and n2 to ann. So you are replacing the first column, which is the coefficients for all the x1s in your system, with the constants. Okay, and similarly, okay, then d of xn is when you have a11, a12, dot dot dot, all the way to b1. You're replacing the last coefficient with the constants. Okay, and then a21, a22, dot 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 to b2. And then down here is an1, an2, dot 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 to bn. Okay, so whichever x you're trying to solve, replace that x's coefficient column with the constant column of b1 through bn. Take the determinant of that, and then that determinant divided by the determinant of the coefficient matrix D will give you the answer to that x, to that specific variable. Okay, so this is how you do it. Okay, now let's look at an example. Okay, I'm just going to do a system of 3 variables with 3 equations. You have 3x minus 2y minus 2z equals -1. And then 3y plus z equals -7. And then x plus y plus 2z equals 0. Now, you can see clearly in the second equation, I have a blank here, which is 0x plus 3y. But since we don't need to write 0x, okay, I didn't write it, but it is a good habit to line up all the x's and all the y's and all the z's when you write the systems of equations. This way, you can clearly see what the coefficients are for each different variable, right? So now, of course, we're trying to solve x, y, and z. So x we know is dx over d, y is dy over d, and z is dz over d. Okay, so let's figure out what d is. D is the determinant of my coefficient matrix. So that is 3x minus 2y minus 2z, then 0x plus 3y plus 1z, and then 1x plus 1y plus 2z. That's all the coefficients I have. And I am going to find the determinant of it. You can see the easiest is to use a 0 in the process like we practiced before. So I can either use the first column or the second row, okay, either one looks pretty much the same because other than 0, the other two elements are 3 and 1 in the first column and the second row. So it doesn't matter. Let's say I pick the second row, okay, so then this equals 0 times this cofactor, okay, and that's just 0, plus now 3 times, so I'm using this 3 right here, okay, and that's 3 times -1 raised to the second row plus the second column, okay, and times its minor, which is getting rid of the second row and the second column like this. So you get 3, -2, and 1 and 2, right? So 3, -2, 1 and 2, okay, plus 1 times -1. So this one is the one I'm talking about, okay, raised to 2 plus 3, then, and getting rid of this one's row and column, you get 3, -2, and 1, 1. So 3, -2, 1, 1. Okay, everybody with me so far, I hope. Okay, so this then equals 0 is 0, this first term, okay, that one we don't have to worry about. The second term, 3 times -1 raised to the 4th power is just 3. Okay, so 3 times, then 3 times 2 minus 1 times -2. That's the determinant of that 2 by 2 matrix, plus 1 times -1 to the 5th power, which is -1. Okay, so this is -1 times, okay, the determinant of that 2 by 2 matrix, which is 3 times 1 minus 1 times -2. Okay, I need to do a bracket here. Okay, and that gives you 3 times, okay, so 3 times 2 here, 6. 6 minus 1 minus negative 1 times 2, -2 is -2. So 6 minus -2 is 6 plus 2. That's 6 times 8 plus -1 times 3 plus 2, which is 5. So that gives you 24 minus 5, which is 19. Okay, so that is your D. That goes into the denominator of all 3 variable solutions. Okay, it's not 0, so that's good news. That means this will have one unique solution to this system. Okay, all right. Okay, so that is the D part. Okay, now let's do dx. Dx is replacing the first column, which is the coefficients of all the x's, with your constants. So instead of 3, 0, and 1, we have -1, -7, and 0. And then the rest are the same. Okay. So we're trying to find the determinants of this matrix. Okay. Again, you can choose the first column or the third row to utilize that 0. I'm going to use the third row here. Okay. So the first term is just 0 because 0 times its cofactor, plus, okay, 1 times -1 raised to the third row and second column times its minor. So that is when you get rid of, right here. Okay, so you have -1, -2, -7, and 1. So -1, -2, -7, and 1, plus the third element in the third row, which is 2 times -1 raised to third row plus third column power times the determinant of its minor, which is -1, -2, -7, and 3. Right, so -1, -2, -7, and 3. Okay, so that equals, okay, 0 is gone, we don't have to worry about it. And then -1 raised to the 5th power right here is -1. So you have -1 times negative 1 times 1 minus negative 7 times negative 2. Okay, so that's the determinant of this 2 by 2 matrix. Okay, plus, okay, here negative 1 raised to the 6th power is positive 1. So we just have 2 times negative 1 times 3 minus negative 7 times negative 2. And that gives you negative 1 times, okay, so that's negative 1 minus positive 14, which gives you negative 15. Okay, negative 1 minus 14 is negative 15 plus 2 times, okay, here's negative 3 minus 14, which is negative 17. Okay, so that gives you positive 15 plus negative 34, which gives you negative 19. Okay, so that's what dx equals to. Okay, now dy is replacing, okay, this column right here with this column of constants. Okay, so that gives us, okay, 3, 0, 1, and then the second column is all the constants, negative 1, negative 7, and 0, and then the third column is the same, negative 2, 1, and 2. Okay, again, you have 2 zeros you can utilize, and I'm going to utilize the third row again because 1 and 2 here are going to be easier to calculate than negative 7 and 1. So this equals 1 times negative 1 raised to the third row plus the first column times its minor, which is deleting these two things. So you get negative 1, negative 2, negative 7, 1, okay, plus 0 times this cofactor 0 plus 2 times negative 1, third row plus third column times its minor. So that's getting rid of these two things. So you get, okay, 3, negative 1, 0, negative 7. Okay, so that equals to, here, negative 1 raised to the 4th power is positive 1. Positive 1 times 1 is still 1. So that just equals 1 times negative 1 times 1 minus negative 7 times negative 2. Okay, plus 0 is gone. Then negative 1 raised to the 6th power is positive 1. So we have 2 times 3 times negative 7 minus 0 times negative 1, so that's just 0. So this gives us negative 1 minus negative 1 minus 14, which is negative 15, plus 2 times, okay, then 3 times negative 7 is negative 21, and negative 21 minus 0 is still negative 21, so that gives you negative, okay, 42 plus 15, so negative 57. Okay, so that is your dy. Okay, finally, dz is when you replace, okay, all the z coefficients right here with all the constants right there. Okay, so let's look at what that looks like. So that is 3, 0, 1, okay, negative 2, 3, 1, then replacing it with the constants in the third column. So negative 1, negative 7, 0. Okay, again, the third row has a 0 and 2 1s, the easiest to calculate. And I'm going to use that. So we have 1 times negative 1 raised to, so this one is what I'm talking about, the third row and first column. So 3 plus 1 times its minor. So that's by deleting its row and its column. You get negative 1, negative 2, negative 1, 3, and negative 7. So negative 2, negative 1, 3, and negative 7. Okay. plus, okay, this 1 times -1 right here, this 1 raised to the third row, second column. So 3 plus 2 times its minor, which is getting rid of these 2 row and column. So you get 3, -1, 0, -7. Then plus 0, that's the third term. So if we do that, okay, again, -1 raised to the 4th power is positive. So positive 1 times positive 1 is just 1. We don't have to write it out. This equals -2 times -7 minus 3 times -1 plus this one, -1 raised to the 5th power is -1. So -1 times, okay, the coefficient of that, this 2 by 2 matrix, not coefficient, sorry, determinant is 3 times -7 minus 0 times -1. Okay, then that is 14 minus let's see, yeah, 14 minus -3, so that is 17 plus, okay, -1 times -27, I mean, sorry, -21, 3 times 7 is 21, okay, and that gives you 17 plus positive 21, which is 38, okay? So now we know x equals dx over d, which is, okay, -19 over 19, okay, so x equals -1, okay, y equals -57, okay, over 19, okay, so -57, and this is d right here, so that's -57 over 19, then z is this one, dz over d, which is 38 over 19, which is +2. Now, again, this is the unique solution to this whole system of equations, and you can plug them all back into these, all 3 of these equations to verify that they do actually work, and they do. I verified it. So now this seems very tedious, and that is because I went very slowly, step by step, trying to show you every single step. But as you become familiar and learn how to do this, you'll be able to speed up and do it quicker and quicker. Okay, so and especially when it comes to solving for a larger system of equations, this is going to be a pretty neat rule to follow. Okay. All right. Okay, so that is 6.3. We've done one of the 2 sections. Okay, so 6.5 is inverses of square matrices. Okay, so first of all, okay, an inverse matrix is also used to help you solve systems of equations or matrix equations, so keep that in mind. Now, first of all, I want you to get used to writing matrix equations, okay? So let's say that you have, okay, 2 equations, which is -x, then plus 5y equals 2. Then x minus 4y equals -1. And if I were to ask you to put this in the matrix equation form, so, okay, so this is different than what you've been seeing as just simply the coefficient matrix and the matrix for for your constants. The matrix equation means you put all the coefficients into one matrix. So it's -3 and 1 for x, and 5 and -4 for y. Then you multiply that by your variable of x and y, and then that gives you the matrix for the constant of 2 and -1. Okay, now you know how to multiply matrices already. So if you were to multiply, the first matrix and the second one, you'll get exactly this system back. Okay, so but we're not trying to get the systems back. We're trying to solve it in the matrix world. So that's why we converted into this matrix equation. Okay, now let's do another quick practice. So let's say you have a system of equations where it's 3y minus x equals -2, 4 minus z plus y equals 5, and then z minus 3x plus 3 equals y minus x. And I want you to change that into your matrix equation. Now, to do that, you can see here, the variables are not lined up, right? You have y, you have z, x is over here, so they're all over the place. So the first thing to do is to change all the equations to their standard forms. Put x, y, z, and then constant on the other side. So this equals -x plus 3y, okay, plus zx. So I'm gonna give you plus 0z, I should say, plus 0z. So I'm gonna give z a spot that equals -2. Now the second equation, okay, has no x in it, so I'm gonna leave that open because this is 0x. Then you have y minus z equals, okay, you move this 4 over to this side of the equation and becomes -4, so that gives you -1. Or sorry, not -1, +1. 5 minus 4 is +1. Okay, then the third equation is when you put this -3x over here, okay, and then z also comes over here, then you get, okay, so +3x minus x is 2x, okay, plus y minus z equals +3. Okay, so now all three equations are in their standard forms, so you can get the matrix equation, which is now the matrix of coefficient, -1, 0, 2, then 3, 1, 1, then 0, -1, -1. That's all the coefficients, okay, times your variable equation, so x, y, and z. And that equals your, okay, constant matrix. So this is your, okay, matrix equations for this system. Okay. All right. So that's just a quick, pointer on what we mean by matrix equations. Now let's talk about, before we talk about inverses of anything, we need to introduce the identity matrix. Okay, so the identity matrix is an n by n matrix. We don't specify how many, but I of n is a n by n matrix. N by n just means it's square. That means it has the same number of rows as columns, okay, where you have ones on the main diagonal and zeros everywhere else. So it looks something like, okay, 1, 0, 0, all the way to 0. The second row gives you 0, 1, 0, dot, 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 0. And third one is 0, 0, 1, dot, 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 0. Then all the way to 0, 0, 0, dot, 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 1. Okay, as the last one. So the main diagonal of your matrix has all the ones, and everywhere else we have zeros. Okay, so this one is called the identity matrix. The identity matrix in the matrix world works as one for any set of real numbers. What we mean by that is, 1 times any number is that number itself. So similarly, if, okay, let's say we have a matrix A that can actually times I, remember we said the number of columns in A must be the same as the number of rows in I, right? Because last week we talked about the rules on how matrices can multiply. Okay, so assuming A is one that can actually multiply with I, then A times I is just A. Okay, and or if you have another matrix that's that's B, you can do I times B. That means B has n rows because I is n by n, right? That still equals B. So I is the identity matrix that whatever it multiplies to equals that other matrix C itself. So it works kind of like one for real numbers. Okay, now with the idea of identity matrix, you can now figure out the inverse, okay, of a matrix. Okay, so we say let A be an n by n matrix, so it has to be a square matrix. Okay, so if there exists an n by n matrix called A inverse raised to the negative, denoted by a -1 super script, then okay, such that okay, A inverse times A gives you the identity matrix, and A times A inverse also equals the identity matrix. Then we call A to the -1 the inverse of A. Okay, so that's how we define the inverse of a matrix. It's denoted by A with a -1 superscript, and it has to satisfy all these conditions we have just listed. Okay, now the way to find the inverse of a matrix is the following. Okay, so what to do is, to find the inverse of a matrix. Okay, so step 1, you want to form an augmented matrix where you list A right here, put a vertical line, and then put the identity matrix right on the other side. Okay, you create this, and both are n by n. So A and I are n by n. Okay, so you just list the two matrices side by side with a vertical line dividing them. Okay, and then step 2 is you use the Gauss-Jordan elimination, okay, and to put A and I into the form I and B. What I mean by that is the Gauss-Jordan elimination, if you remember, is to reduce a matrix to its reduced row echelon form, which is now as the identity matrix, right? So you do whatever it takes to turn this A into I, but you allow the same row operations. Whatever you're doing to A, you do it to I on the right-hand side. And by the time you turn A into this I, then on the right-hand side, the I is no longer B and I. So we call it B now. And if, of course, if possible, okay? Because sometimes A just simply cannot be reduced to an identity matrix, okay? If that's the case, then, okay, A inverse is B, or I should say B is A's inverse, okay? So let me again show you an example of how this works. Let's start with a 2 by 2, really easy one, okay? So let's say we have A equals 2, -3, -1, 2, and I want you to find its inverse, okay? The way to do it is you create an augmented matrix. You list A on one side, then do a vertical line and do a identity matrix with the same order on this side. So it's 2 by 2 identity matrix. Now your goal is to turn this side into an identity matrix, and then whatever the right side ended up being is going to be your inverse. Okay, so let's say, well, to do this, I know I need to make turn the first number right here, 2, into a 1. Well, if I add the second row to the first one, if I add -1 to 2, that will turn 2 into a 1, right? So I do okay. So I do R2 added to R1, right? So whichever row is listed second, that means that's the row you're making changes to. So R2 added to R1 will give you 1. Then this is -1, because -3 plus 2 is -1. And then you didn't do anything to the second row, so this equals the same. Now, on the right-hand side, you do exactly the same you just did, and by this same operation here, right? So here, 1 plus 0 is still 1. Then the second number, 0 plus 1, okay, so that has become 1. Then you didn't do anything to the second row, so that remains the same. So your row operation was to change this row, but as a result, you did exactly the same operation on this row as well. So both have the same row operation happen to both sides of this augmented equation matrix. Okay. So now you can see, well, I want to make sure these two numbers need to be 0, and then this 2 needs to be a 1, right? So that's what you need to do. And well, you can see if I add 1 to -1, I'm going to turn this into a 0. If I put this number right added to that number, that will make my -1 turn to 0. So let's do that. Let's say you get, okay, now R1 added to R2, okay? So that means the change is in R2. So -1 doesn't change. Now the second row, -1 plus 1 is 0. Then 2 plus -1 is 1. Okay, oops. Okay. Then you do the same thing you did here, where 0 plus 1 is 1, and 1 plus 1 is 2. And then you didn't do anything to change row 1. Okay, so again, same row operation right here applied to both sides of the augmented matrix. You did exactly the same row operations on these two different matrices that you put together. Okay, so now you can see this is really close. All you need to do on the left-hand side is to turn this number, -1, into a 0. Then you'll have your identity matrix on the left-hand side. Well, to do that, you can see if -1 is added with 1, that will turn it into 0, right? So let's do that. Let's say, okay, this is R2 added to R1, okay? And then you get 1 plus 0, so these two, 0 added to 1 right there is still 1, okay? And then the second number is 1 added to -1. That turns you into 0. And you didn't do anything to row 2, so that's the same. And over here, 1 added to 1, okay, gives you 2. Then 2 added to 1 gives you 3, and then you didn't do anything to the second row right there. Excuse me. Now, on the left-hand side, this is your identity matrix. So that means this is your inverse. Okay, so that tells you the A inverse is 2, 3, 1, 2. Okay, now if you want to verify, okay, then remember A inverse times A must equal 1, 0, 0, 1, right? So we can verify if that's the case. And so this is 2, 3, 1, 2 times, okay, 2, -3, -1, 2. That equals, okay, so the first element here equals 2 times 2 plus 3 times -1, right? Because it's these two multiplied plus these two multiplied. That's how the multiplication works, if you remember. And if you do that, you can see that is 4 minus 3. So 4 minus 3 is indeed 1. Okay, then the second element in the first row is 2 times -3 plus, okay, 3 times 2. It is this number multiplied with this number plus this number multiplied with this number. Okay, so again, if you do the math, it's -6 plus +6. So that is indeed, okay, 0. Now, right here, that spot right there, the second row, first column, equals to, okay, 1 times 2 plus 2 times -1, right? Because it's this number times this number plus this number times that number. That's how we got that, right? And that's, again, how matrices multiply each other. And that is 2 minus 2, which is 0. Okay, then finally, the last number in here is this number times this number plus this number times this number. And if you do the math, it indeed gives you +1. Okay, so then you need to verify A times A inverse also equals 1, 0, 0, 1. And I'll leave you to do that yourself, and you'll find that that is indeed the case. So our solution is correct. Okay. All right. Okay. Now, okay, we have looked at this with the common method. If you are talking about an inverse of a 2x2 matrix, again, just like the determinants, we have a quick trick or rule of thumb. So for inverse of a 2x2 matrix, okay, so let A, B, C, and D, right? Then A inverse is going to be 1 divided by the determinant of A, okay, times D, -B, -C, and A. Okay, so what we did was we switched the order right here, okay, from this original order. We swapped the two spots on the main diagonal, okay, and then we multiplied the other diagonal terms by -1. That's how you get negative in these two cases, in the two spots, okay? So, okay, and then multiplied by 1 divided by a determinant, okay? Now here, realize that this is a constant multiplied by a matrix here. This is a matrix, okay? So that means this constant needs to be multiplied to every single term. It's not from a row or a column, like when you can pull a common factor out of a row or column out of a determinant, right? So the bracket is not the same as the two vertical lines. Remember that. For a bracket, a constant times, everything is multiplied to every element, okay, when you multiply it in. But for the determinants, that's pulled out of one specific row or column, okay? So keep that in mind. Brackets, different than vertical lines, okay? Now, of course, okay, you can see again the determinant is in the denominator. So this means, okay, A inverse exists only if and only if, I should say, if and only if the determinant is not 0. Okay, if determinant is 0, then the inverse is undefined and doesn't exist. Okay, or another word, you can say that A is invertible if A inverse exists, or not invertible if A inverse does not exist. Okay, so again, let's look at some examples. Okay. So let's find the matrices, find the inverses of the following matrices, okay? So A, you have A equals 3, -5, 2, and 1. Instead of going through what we did previously, augmenting and, with the augmented matrix and trying to turn the left side into identity and see what the right side is, now you know A inverse equals 1 over the determinant of A times, okay, 1, 3, swap the main diagonal terms and elements, then turn the other diagonal elements to its negative, okay? So then we just need to find out what A determinant is, and A determinant is 3 times 1 minus 2 times -5, okay, which is 3 plus 10, which is 13. So that tells you the A inverse is 1 over 13 times 1, 5, -2, bracket 1, 5, -2, and 3. You can leave it like this, or you can multiply it all in, where you turn this into 1 over 13, okay, 5 over 13, -2 over 13, and 3 over 13. Okay, because this is a bracket, it's a matrix. You can multiply a constant into every single element. Okay, so either way is correct. Okay, and of course, if I were you, I would go verify A inverse times A is indeed identity, and A times A inverse is indeed identity, right? So you need to verify that to make sure you got it right, and I'll leave that to you. Okay, let's look at another example, right? Let's say that you have a bigger matrix. Okay, it's 2, 4, 2, -1, 5, -1, 3, 1, 3, right? Only square matrices can have inverses, so it's a 3 by 3. Now let's figure out how to get this one to turn out to be the inverse. So this one, there's no trick, unfortunately. You have to use the augmented matrix approach that we were doing. So you'll do 2, 4, 2, -1, 5, -1, 3, 1, 3 on this side. Divide it into half, then do 1, 0, 0, 0, 1, 0, 0, 0, 1. The identity 3 by 3 identity matrix. Okay. Again, your goal is to turn this side into the identity matrix, but do exactly the same row operations on this side, and whatever the right side becomes, it is your excuse me, inverse. Okay, so let's look at it. Okay, now to do this, okay, I need to make these two numbers zeros, right? And in fact, I need to make all these numbers zeros right here, and then the main diagonal from 253 to 111. Okay, so let's work on that. So first, I want to do 2 row operations. I want to add R2 to R1. That will make this 2 into a 1. Okay, but then I'll do 3 of R2. Okay, plus R3. That will turn this 3 into a 0. Okay, so let's do that. And R2 added to R1 will turn into 1. Okay, 4 plus 5 is 9. 2 plus -1 is 1. Then we didn't change R2 at all, so that didn't change. And then we did 3 R2 added to R3, so 3 plus -3 is 0. 1 plus 15 is 16. 3 plus -3 is 0. And over here, okay, we added R2 to R1 as well. So 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. And we didn't change the second row, but then the third row, we did -3 times the second row to the third. So 0 plus 0 is 0. Then 0 plus -3 is -3. Then 1 plus 0 is still 1. Okay, so you can see the right-hand side is already, okay, changing. Oh, wait, sorry, it's not -3 here. Okay, we just did 3 times R2, not -3 times R2. So this is +3. Okay, so now I want to change, this -1 into a 0, and I can do that by adding row 1 to row 2. So I'll just do R1 added to R2. That gives me 1, 9, 1. Then -1 plus 1 is 0. 5 plus 9 is 14. -1 plus 1 is 0. Then I have 0, 16, 0. Here, 1, 1, 0 doesn't change, but then 0 plus 1 is 1. 1 plus 1 is 2. 0 plus 0 is 0. Then 0, 3, 1. Okay. Now, okay, I want to change this number to a 1, right? 14 to a 1. So I'll do 1/14 times R2. That gives me 1, 9, 1, 0, 1, 0. Okay, and I didn't do anything to the third row, so 0, 16, 0. And over here is 1, 1, 0. The second row is multiplied by 14, so now you have 14 or 1 over 14. Then 2 over 14 is 1 over 7. Then 0, 0, 3, 1. Oops. Okay, so that is this one. The next step is that I want to, okay, turn this number 16 into a 0. So to do that, okay, I do -16 times R2 plus row 3. And that gives me, okay, 1, 9, 1. That doesn't get affected. 0, 1, 0 is not affected. Then here, 0 plus 0, 0. 16 plus -16, 0. And then 0 plus 0 is still 0. Okay, and over here, 1, 1, 0. 1 over 14, 1 over 7, 0. Then 0 plus -16 times 1 over 14 gives you -8 over 7. Okay, then 3 plus -16 times 1/7 will give you 5/7. And then 1 plus 0 is still 1. Okay, now here you can see all of a sudden we have a row of all zeros. Okay, and if you hit a row of all zeros, then that means there's no way you can turn it into, okay, 0, 0, 1 anymore. And this then tells you this matrix is not invertible. Okay, it's not invertible. Okay, all right. So, okay, now let's tie the whole inverse idea into something useful. When we're trying to solve a linear system of n equations with n variables, okay, we can actually use the inverse matrix to help us. So this is called the inverse matrix method. Okay, now to do this, okay, so step one is you write the system in the matrix form for your n. So you have a n equations with n variables. Okay, so you want to write it into a times x equals b, where a is the coefficient matrix, okay, and x is the variable matrix, okay, then b is your constant matrix. Okay, so you write it into the matrix equation form I showed you a few minutes ago. And then what you do is you calculate okay, the inverse of A, okay, if it exists. Okay, and if A inverse does not exist, okay, the system either has infinite number of solutions or no solution, and a different method is required. Okay, so the system is either dependent or inconsistent. Then you have to use some other way to solve it and see which one it is, okay? But step three is that, well, since you have ax equals b, then you multiply both sides, okay, by A inverse. Then you get A inverse times AX equals A inverse times B. And remember, A inverse times A is just I times X equals A inverse times B. And I times X is just X itself, that A equals A inverse times B. Okay, because I is the one in the matrix world, right? And so then that means, well, all you need to do is to find the matrix of A inverse times B. And this is going to be a n by 1 matrix because A is n by n and B is n by 1. So that means, you know, A inverse B is going to be n by 1. Okay. And that is going to be the solution for your x, because x is also n by 1. It's just all the n variables you have. So then that would have solved your, okay, your whole system. Okay. Now, the one thing I want you to remember is that when you do step 3, always put A inverse on the left of all the other matrices. Okay, because A inverse times B is not B times A inverse, right? Because the matrices, you know, the order matters. So you always put it on the left-hand side of the other existing matrices. Okay, now let's do a couple of examples. Okay, really quick, and then I'll let you go rest your head because I'm sure your head hurts. Okay. So let's say you have a system is 4x minus 5y equals 3, then negative 3x plus 7y equals 1. So to solve this using the inverse matrix method, right? First of all, we want to turn this into the matrix equation. So that's 4, -5, -3, 7 times xy, okay, equals 3 and 1, okay? Now, this, if we call this first matrix A, this matrix X, this matrix B, then we want to find what A inverse equals to. And since this is a 2 by 2, that we know that equals 1 over A determinant times, okay, 7 and 4 switch to places, and then 3 and 5 become the negative term of what they were before. And so then A determinant is 4 times 7 minus -3 times -5. And that gives you 28 minus 15, which is 13. So you get 1 over 13 times 7, 5, 3, 4. Okay, so that's what A inverse is. Okay, so that means your x and y equals A inverse times B, which is, okay, 7 over 13. We just multiply the 1 over 13 inside the whole matrix. 5 over 13. Okay, 3 over 13 and 4 over 13 times your constant matrix. That gives you, okay, the first number is this times this plus this times this, right? That's how matrices multiplication works. So that gives you, okay, see, 3 times 7 over 13 plus 5 over 13, that is 21 over 13 plus 5 over 13, which is 26 over 13, which is 2. So that's 2, okay? Then the second number in this equation equals this number times that number plus this number times this number, right? That gives you the second term. And so that equals 3 times 3 over 13 plus 1 times 4 over 13. If you do that, that equals 13 over 13, which is 1. So that tells you x equals 2 and y equals 1. Okay, so, or you can leave it as, you know, x, y equals 2 and 1. That's fine as well. Okay, so that's how you use this method to solve it. Okay, and now you can plug x and y, of course, into these two original equations to make sure they actually both hold. And in this case, they do. And but you can verify that on your own. Okay. Now, another quick example. Okay, let's say you have a system of equation that is -x plus 2y equals 3, then 3x minus 6y equals -5, and use the same system inverse matrix method to solve it. So first we want to change into matrix equation system format. You have -1, 2, 3, -6 times x and y equals 3 and -5, right? And then we need to find A inverse, which is 1 over A determinant times, okay, -6, -1, then -3, -2. Right, again, just switching the main diagonal elements and then turning the negatives on the off diagonal terms, okay, elements. Well, so that means we need to find what a determinant is, which is -1 times -6, okay, minus 3 times 2. And if you do that, this tells you this equals 0. So this equals 0 means A is not invertible, okay, which means this system either is dependent, meaning it has an infinite number of equations, or it is inconsistent, meaning there's no solution. Okay, and then you have to find a different method to solve this, and we have talked about plenty other methods to solve the system of equations. And if you try to solve this, I believe you'll find that this is inconsistent. It's not gonna, there's no solution to this system at all. Okay. All right, so that's plenty new knowledge and examples. I hope you do a lot of practice, because the only way to get this down is to do a lot of practice. And if you do that, you'll get this. And when you get to statistics, and especially econometrics, your life will be much, much easier. And this is going to be the most important applicable part of your economics training, because it essentially teaches you how to solve, how to analyze data. Because when you do data analyses and the different models, especially the most useful and most commonly used model for undergrads is a system of linear equations, and you're trying to solve that whole system. So it's all linear algebra essentially for most of your 388 that you're doing. So anyway, practice lots and write down your questions, and we'll talk about your questions on Thursday.